Hello students, this is Brock Skaggs. So I'm going to make this video showing how to use SageMathCloud to help us in our kinematics class. And so specifically we're going to focus in on this example here. And so we've got an inline slider crank. We're not going to study all the kinematics of it as far as trying to relate the motion of the crank here with the oscillating motion of the slider, but we're just going to focus in on describing the motion of the crank itself. And so that's going to require us to perform an integral as well as take the derivative of this function here. And so that's what we're going to show as being able to be done inside of Sage there. And so our input that we have is that we know that the angular velocity of link 2 here, which is the crank, is going to be described as 55 times t squared, where the units are in degrees per second there, and t of course is their time parameter. We also know that the initial position, so before we start this mechanism, we're going to set the crank to an angle of 30 degrees above the horizontal there, so theta 2 starts off at 30 degrees at time equals 0. And so we know the angular velocity of the crank, but what about the angular position and angular accelerations? And so hopefully we're able to use Sage in order to determine those expressions for these two variables here. And so let's go ahead and go into Sage now. So at this point I haven't done much. In Sage I've defined a time variable t. This salvus line here and the return line is just in order to get this so I can click on it and have the image here in the hyperlink there. The big ones though for the actual workings of this problem is the fact that hey, I'm defining a symbolic variable t for time there on line 4. You can see the comment line for inputs and also the comment line here for the initial condition, and then here I'm describing the angular velocity there, 55 times time squared there, and that angular velocity, omega under 2 variable, as you can see, is a symbolic expression there. And so we should be able to work with that as we work through this problem. And so we've got two different ways to go. One way is we have to integrate from that angular velocity to get to angular position. And then the other way is we go from angular velocity and we take the derivative of it with respect to time to get to angular acceleration. Because in the back of our minds, hopefully you're thinking that from position you take one derivative to get to angular velocity. From angular velocity you take another derivative to get to angular acceleration there. And of course we're always taking the derivative there with respect to time. And so let's first work on the angular position. So I'll just type angular position calculations here. So we know that this block of code is going to be devoted to it. And so one thing I know about it is when I take that integral, I'm going to have to deal with this integration constant there. We don't have limits on this integral that we're thinking about. And so we're going to have some C1 variable. And I'll just call it C underscore 1 and define it as a symbolic variable here. Next, what we can do is we can actually determine the part of the integral without the integration constant. And so I'll just go ahead and put a comment line to describe this. We're going to determine the theta underscore 2 without integration constant. And how we're going to do that is we're just going to say theta underscore 2 for the variable. I'll just make sure I put no constant as well in there. That way I don't forget to worry about it. And then here we're going to say, well, let's integrate. It's just a keyword inside of Sage. What are we integrating? Well, we're integrating omega underscore 2. That's this symbolic expression above. And what are we integrating with respect to? Well, we're integrating with respect to time there. And so that should give us a expression there. I just hit Shift Enter, that evaluated it. At this point we're not seeing anything, but I could quickly say, let's print a line here that says theta underscore 2, no constant, or no integration constant. And then we'll say show theta underscore 2. Notice here I can just hit tab at that point and it auto-completed for me because it already knows what theta underscore 2 underscore no constant is. And so using that show command on line 15 generates this output right here, and you can see part of the integral is going to be 55 divided by 3 times t cubed there. And so now we just have to worry about the integration constant. And so how you obtain the integration constant here is that you have to know something about the initial condition here. And so our initial condition is that theta 2 at time equals 0 is equal to 30 degrees there. And so we're going to have to basically solve for the C1 because we know it's 55 over 3 t cubed plus some C1 value is going to equal to 30 degrees when t is equal to 0. And so I'll just write that as initial condition as a variable name here. And so we'll say that initial condition variable is going to hold the expression for us. It'll be theta underscore 2 underscore no constant. And here we want to substitute the value 0 for this t. And so I'll just type in substitute, or partially hit substitute, and then just hit tab there so I can select substitute. And I would say, well, we want to substitute t equals 0, and then we'll add in c underscore 1, and we know that that all has to equal 30 degrees there. And just to make sure we are on good footing here, the initial condition is not defined. Did I misspell it? I did indeed. And you can see that initial condition is still an expression. We should also be able to show that just to make sure we understand what we're doing there. And we show it, it's already solving for us because everything's going to be on the left-hand side is going to 0, so that's why it's saying C1 is equal to 30. But it's not always going to be the case there, that's going to go straight to our value. And so I want to get in the habit of solving this, because here you've got this portion here is when 55 over 3, and we're setting t equal to 0 cubed, and then think of that as plus C1, and then on the right-hand side we have equals 30. And so really I want to get in the habit of solving that for C1. And so I'll just use a variable solution to hold the output of this solve function. And so if you've watched the other videos, you know how solve works. You basically pass it in the equation you want it to solve. So that equation is going to be my initial condition, and I want to solve for C1. And here I'm going to try another thing as well. I'm going to set the option solution under dict equal to true and solve it. Argument solution underscore dict. There we go. No capitalization on the D there is what that error was for. And what that does is allows me to look at the solution a little bit differently. Here I've solved for the solution, and I'm on line 18 I'm just saying show it. And so C1 is going to be assigned the value 30. And so 30 degrees is equal to C1, that integration constant. If you went to type right now on solution, you would see that it is a list. Right there, it is showing it's a list. And so we want to get the dictionary out of the list. And so I'm just going to put solution underscore dict is equal to the first element in the solution. So that's element 0 here. And so I'll say show here solution, and I'll put a line of parent above it just for clarity. The list version of the solution. And then here we'll say the dictionary version of the solution. Except I need to show that there. And so basically what we have here coming right out of the solve command is a list of dictionary items. There's just a list of one item in there, so that's where I'm saying grab the first item in the list. I know it's going to be of type dictionary. And then we just have to get the C value out of the dictionary. And so to do that, you can just say C underscore 1 is equal to the solution underscore dict, because that is the dictionary variable there. And then for the dictionary, you want to put in the key value here to get the value out. And so the key is just what's left of the colon here, and so that's just C underscore 1 as well. And so I'll just type in C underscore 1 there. Notice I didn't get any syntax errors there. And so finally I can say print integration constant value. And here I'll print in the same line is C underscore 1. And so this very last bit of output here, you can see the integration constant value is 30. And so I finally got that 30 value out. And so the only thing left to do is basically combine this. And so we have this 55 over 3 t cubed, but this really needs to be plus 30 in order to be the actual position function for us. And so I'm going to say theta underscore 2 is equal to theta underscore 2 no constant plus my c underscore 1 value. And I'll say print complete position function. And I'll say show theta underscore 2. And so this very last line is the complete function, or what it looks like as an expression here, for the angular position. And so again, basically the way we've done that is we know the angular velocity. We know that you have to integrate that with respect to time to get the angular position. And then the last bit is to take care of the integration constant there. And so we've got the angular position, so we're halfway done. Remember the PowerPoint here, we were trying to get angular position, which is what we just did, and as well as angular acceleration. And so from the angular velocity, we should just be able to take one derivative with respect to time to get to angular acceleration. And so our work won't be quite as long for this second part. And so to do this, what we'll do is we'll say comment here angular acceleration calculation. And here, let's define a variable. We'll call it alpha underscore 2 for that angular acceleration. And so that's going to equal diff. Differentiation is short for diff here. What are we taking the derivative of? Well, we're taking the derivative of this expression here, omega underscore 2. And so we just type in here omega underscore 2. And what are we taking the derivative with? Well, we're putting comma with respect to time here. And I'll just say print here angular acceleration result. And I'll say let's show alpha underscore 2. And so you can see here the result is 110 times t, which I believe is correct there. This one's a fairly simple one, right? You can basically take the derivative of that hopefully in your head, just a power raised to an exponent there. So the exponent comes down, so it's 2 times 55, and then the exponent drops by a power of 1, and so just leaving t there, so 110t does sound correct there. And so one thing I'll do finally is just do a little bit of housekeeping here. Oops, I lost my work there. I'll just retype it real quick. It's not defined, so we'll just hit Control A, select all, and run. And there we go. Since I did lose my work, let's go ahead and put a summary statement here. And so I'll say print here summary of motion of crank, which is that member that we're talking about. And so we can say things like position in units of degrees per second. Missing the print there. And then we'll show theta underscore 2. And then we'll print a line that says velocity in units per degrees per second. Oops. Position will just be in degrees. My bad. And so we'll show omega underscore 2. And then finally we'll print and say acceleration with units of degrees per second squared. And we'll show alpha underscore 2. And print those values. And so now we've got this nice, very neat and organized block here on line 42 showing us the angular position of the crank, 55/3 times t cubed plus 30, the angular velocity, 55 times t squared, as well as the angular acceleration here, 110 times t, for the motion of, again, this crank here, given these inputs. And so in this video, we're able to show a little bit of the calculus that Sage can do here. We're doing some very simple integration and some very simple differentiation there, and setting it to use in our kinematics class. And so thank you for watching the video. Hopefully this helps you understand both Sage as well as our kinematics topics.